Hello, welcome back to my channel. In the previous video, I showed you how to calculate the time period and the frequency of an unstable multivibrator. So in this video, I'm going to, go into rectification as the process of converting AC signal to DC signal. So please don't forget to like this video, share it, and also give a comment there so that I can be able to improve on the new content. Thank you so much. Let's go ahead. As I said earlier, a rectification is the process of converting AC signal to a DC signal using rectifier channel. Types of rectifier. One, we have half-wave rectifier, we have full-wave rectifier, and we have a full-wave bridge rectifier. Alright, okay. Now before we proceed, we have to look at what is a diode. A diode as a channel of a rectification. Yes, a diode, it is an electrical component that allows flow of current or electrons in one direction only. Now here is the symbol of our diode. We have here the anode, which is represented by letter A, and it is the positive terminal of the diode. And we have the cathode side, which is represented by C, and it is the negative part of the diode. And here is the structural behavior or structural diagram of a diode. So here it is the anode, here is the cathode, and here we have a barrier gap here. So for this diode to conduct electricity, this barrier here must be overcome. Now we have diode biasing. Now by biasing a diode, we have two ways of biasing it. We have one here, forward biasing, which is you connect the positive terminal of the diode to the positive terminal of the battery. You also connect the negative, that's the cathode terminal of the diode, to the negative terminal of the battery. So by doing this now, when we come back here, it will allow current or the hole here. Now this one, they are called holes. So it will now flow in this side, while these very electrons here, they will flow to the other side here. By so doing, they will now overcome this depletion gap here or a barrier gap here, whereby making this diode to conduct electricity. So in this case now, the currents will tend to flow this way, or we can call them hole, flow this way, whereby the electrons now will flow in opposite way. Now the reason is because like charges, they repel each other, while unlike charges attract each other. So here we have positive, so the battery here we repel this here, so it now moves in the other direction. Here the same thing, we repel this now. For this reason now, the hole here now will attract to the negative here, then the electrons here now will attract to the positive side, which is unlike charges, what they attract each other. Yes, in this case here, we're going to experience a high flows of current, and also in this case we can in this circuit here, it is what conducting. The diode here is conducting. Okay, now the second bias seen here is a reverse biasing of a diode. In reverse biasing, we connect the anode of the diode to the negative part of the battery, and at the cathode to the positive terminal of the battery here. So in this case here, what will happen is that there will not be flow of electron across the diode here. So in this case, what will happen is that there will be a low current flows here. Yes, because if you see here is positive, here is negative, so it will attract here, and here is positive, here is negative. They will attract here, so there is no how this depletion gap here will be broken. Yes, so in this case now there will not be conduction between the two junction here. Yes, there will not be conduction here. So in this case now what will happen is that this depletion gap will even increase, yes, and making it to become a non-conductor. So in this case we said the diode is what is not conducting. That's just it. Okay, now that we understand how diode works, now we can now dive into our rectification or types of the rectifier we have here. Let's start with number one here. We have a half-wave rectifier. So in half-wave rectifier, this is the schematic diagram of how it looks like. Here we have our AC signal. Yes, we all know that it moves in sinusoidal wave. And we have our transformer here. Let's assume it's a step-down transformer. Yes. Then we have our diode here connected to the only one, the positive terminal of the, let me say the live terminal of the transformer here. So in this case here, we're going to have this signal here passing through this diode here. So what are we going to have as our output here? We'll be having positive and negative. So this is our output signal here. So in this case now, since we have a diode here, it will allow this to flow here this way. Yes, and remember it doesn't allow the flow of current in opposite way, so only one cycle we pass through. So the second one here will be vacant, and the third one same thing. So we're going to have something like this. Yes, continuously. So in this case now, we call this here our pole setting DC. Yes, so here we have our DC. Yes. Alright, but looking at this here, there's a loss of energy here because we just having one pulse here. It is not continuous. So for us to now solve this problem here, we now introduce full wave bridge rectifier. So in this case here, we are going to have two diodes. Here we call this D1 and here is our D2, and we're going to have a center type transformer. So in this case here we have our AC signal. So when it moves other way around, we have this current flows through here this way. So the second one here, when it moves the other way around, it comes through here and it passes through here. So what will be our output here? It will be this way, this way, this way. You're going to have this. Yes, this is how it looks like. So when the signal moves through here, oscillates here, we have current flows through here, passes through here. When it comes the other way around here, it moves through here and it passes through here, and we have our ground here. Yes. So in this case now you can see that we have our signal here now continuously. There is no any missing out here. So in this case now we're going to have our DC here in this one here called setting DC. Now for us to correct this very signal here, we can introduce filter which is not, yes, we can introduce filter which is a capacitor here, positive here and negative here. So by introducing a filter here now, we're going to have, instead of having something this way, now we're going to have this way, which is better than this very one here. Okay, all right. We also have here full wave bridge rectifier here. Yes, this is the complex one and it is the most reliable one commonly used. So in this case here we have our AC here. Yes, then our transformer, connected to our transformer here. Now we have a series of diode here, D1, D2, oh sorry, let's call this one D1, and here we call this D2, and here will be our D3, and here will be our D4. Yes, so we have a series of diodes here, we have series of diodes here, and they are connected in parallel. Alright, how does it works? Now when we have a signal, AC signal here, it induced here, what will happen is that it comes through here, it passes through D1. When it comes here now, it will no more be in an AC signal form again, but rather in one direction, this way. Okay, now as it passes this way now, it cannot pass through here because here is forward bias, sorry, reverse bias, and D1 is forward bias, so it will follow through here to here, this way, and when it comes to here, as it moves through here now, electrons now will move through here, through here, through here, through this part to this part here. Okay, then in the second oscillation here, when the signal moves this way, it passes through here, induced through here, it now comes here, it will now pass through D4 here, this way, this way, this way. Yes, then electrons will now flow through D3 to this side here. Yes, Now these two, at this point now D2 will not conduct. D2 and D1 will not conduct because they are reverse biased. So in this case here, the output behavior looks something this way. The same thing as for that full wave rectifier. So we have it this way here. Yes. Now, whenever we place our filter here, positive, negative here, please be mindful of the polarity. What will happen here? This pulsating DC now will be corrected to be a direct or straight DC. So in this case here, our output here will be DC, not AC. So this is how we convert AC signal to a DC signal. Period. So you can also construct your own power supply. Our appliances, they need DC, but we having AC. What are we going to do? By this process now, we can now convert our AC signal to DC signal. So you can use a transformer here, a step-down transformer, to do that and construct. Alright, thank you so much for watching. In the next video, I'm going to show you the construction, how we can construct half-wave bridge rectifier, full wave bridge rectifier, half-wave rectifier, full wave rectifier, and full wave bridge rectifier, how they work practically, and we're going to test them. Thank you so much. Please don't forget to like the video and share. Also leave a comment below. Thank you so much. See you next time.